Welcome to part 4. Today, value at risk. Value at risk, one of the key financial risk metrics. It consists of two parts, the inverse CDF at alpha and the volatility. We already have the code to calculate the volatility, so today we will focus on the inverse CDF. For the inverse CDF, you need the CDF, and for the CDF, you need to numerically integrate the PDFs. So we'll start with implementing the PDFs in the code. You can use the PDFs provided by SciPy if they exist, but for some distributions they do not exist, so you have to code them yourself. For example, the EGB2 distribution does not have a PDF provided by SciPy, so we need to code it. I will paste it, you can copy it if you want. And we need to import the beta function. Now, just like with the log PDFs, we have to make a general PDF function like this, and we say if distribution is equal to the normal distribution, return its PDF, etc., for the other distributions. Let's go on with the CDF function. So as input we want theta, we want to the distribution, we want to know until where we have to integrate, which is x, and we want to have a lower bound, as using NumPy.infinity as lower bounds, lower bounds will sometimes result in errors in the PDFs provided by SciPy. We will use -100 as lower bound since the PDFs are already 0 there, so it doesn't matter for the integration. Now, numerical integration can be done with a SciPy library named quad, so we need to import this. From the integrate library, return quad. We need the function here, so we just lambda that the PDF theta, the distribution, and z, this is what we integrate over, and we want to go from the lower bound to x. We can test this, for example, with the normal distribution. Let's go in this for now. Print the CDF of the, let's think of any theta, it doesn't matter for the normal distribution. Let's say we want to integrate to 100. The CDF at this level should be 1, since then you integrated over all the mass of the PDF. We see indeed it is 1, and I see we still need to change a bit of our function. We need to only import the first part. So 0. Now we see it returns 1, so we know it works. Now let's go further with the inverse CDF. We again have the arguments theta and distribution. We'll call alpha the value we evaluate the CDF at. We again need a lower bound on the CDF, which we again set at minus 100. And we need to set a lower bound to the x values of the inverse CDF. We will take minus 10 and 10. This is usable for really any distribution if you do not have a really large variance. So the lower bound on x is minus 10, the upper bound on x is 10. Then we define an equation. We want this equation to be 0. And this equation is the CDF x minus alpha is 0. This intuitively makes sense since we want to know the x value where this equation is 0, and we will solve this equation with a solver, but first let's take the equation. Lambda z in the CDF theta distribution z, and again the lower bound is the lower bound of the CDF, that one, and then minus alpha. Now solve this equation. We'll do this with a function that's called brand_q. We also need to import this. It's from the SciPy.optimize library. This function will return an x value, the value we want, and it will give some more results if it has converged or not, which are also important. So brand_q. Which function do we want to evaluate? We need to define this equation, of course. We want to evaluate the equation. This brand_q function will find the x value where this equation is 0, between the lower bound of x, we said, and the upper bound of x. And to make sure we get the full result, also whether it has converged or not, we need to say full output is true. And then we can see if result, if not, result converged. This is not good, of course. We want to print a warning message. Nonetheless, we return the x value. We can test this inverse CDF function. Let's print. Again, you can use any theta as we do it with the normal distribution. Let's say you want the 95 percentile, so 0.95. We know this is 1.64. We do not change the lower bounds, so let's test. And here we see it is 1.64, so we conclude this works. Now we can implement our value at risk, and we will do this in this GARCH. So a commonly used level of value at risk is these 5% level, so called 0.05. It's the inverse CDF with the theta we optimized earlier, so theta ml, the distribution that's imported in this function, the alpha level at 0.05. The lower and upper bounds we don't change, and we will multiply this with the square root of the conditional variance, which is the volatility. like that, and we will implement it in the plot. Value at risk 005. Label is 5% value at risk. Let's check the plots. This looks reasonable. And as we see, the value at risk changes from model to model as the 0.05 percentile of the CDF is different. We see the generalized error distribution as a lower value at risk with more value at risk violations than the D distribution we just saw. So that was it for this tutorial. I hope you learned something. For any questions, please put them in the description. And keep in mind, you can also find the code on the GitHub page. Thank you.